Capillaries are the smallest of the vessels, and capillaries operate in networks or beds, right? They don't act alone. They're very thin walled, very fragile, and they only have a tunica interna. There is no tunica media, there is no tunica externa. This thinness allows them to permit nutrient and gas exchange through them. So they're thin enough, there's small enough distance to allow exchange. Capillaries are just wide enough, just, to accommodate one correctly shaped erythrocyte. Sometimes you can see a capillary with like little red blood cells kind of like lined up as if they're waiting to get on a bus. The other thing is that the pressure in capillaries is quite low, and flow through a capillary bed is it's usually pulsatile, surging and stopping, surging and stopping. This diagram shows a river flowing very fast and then hitting a delta with lots of tributaries that fan out from the main river. And many of us instinctively know that when the fast flowing river hits the delta, the water loses speed. And this is the same situation in your capillary beds. This happens because capillaries, despite the fact that each individual capillary is small in diameter, collectively they have a large combined surface area. So like if I were to take the diameter of all of the capillaries here and add it together. So blood flow slows down in capillaries due to this increased collective surface area. So capillaries are fed by an arteriole and capillaries are drained by a venule. Running through the center, connecting the arteriole and venule, is something called the thoroughfare channel, which is not well pictured in my choice of a capillary bed here, but it would be a vessel that just kind of flows from the arteriole to the venule. So that's the thoroughfare channel. When blood enters this thoroughfare channel, it slows down as it diffuses out into the capillary bed. But controlling blood flow to the capillaries are these muscular valves on this side of the bed that are called precapillary sphincters. And they're like open close valves, and they're only on the arterial side of the bed. When the precapillary sphincters constrict, blood shunts through the thoroughfare channel and bypasses the capillary bed. When you are exercising, blood is shunting through the capillary beds in your digestive system because you don't really need to digest a turkey sandwich while you're running a marathon. But the skeletal muscles will have open precapillary sphincters, allowing blood to perfuse into the capillary beds of skeletal muscle. So the flow through capillary beds, because it is so far from the heart, it's pulsatile, and that is what is called vasomotion. Erythrocytes kind of like lurch along in big steps as the heart pumps and relaxes and pumps and relaxes. And this slowness, it allows oxygen and carbon dioxide and other nutrients to be exchanged. So like think of your erythrocytes as like a train making stops along the way, not just speeding through all the stations. Okay, so I talked about this a little bit in the previous slide. When we consider the surface area of our blood vessels, or like the diameter, we do this by considering the cumulative surface area or diameter. So if I'm going to talk about muscular arteries, I'm going to talk about the diameter of all of them added together, not an average, added together. So theoretically, if we take all the vessels of one type, like all of your capillaries, all of your venules, and if we add together all of their diameters, then we would have a cumulative surface area. Arterioles would have the smallest cumulative surface area. And this is what leads them to be resistance vessels. capillaries would have the largest because there's so many of them. Even though veins have a greater diameter, there's so many capillaries. If you add them all together, it's more than your veins. So by the time your blood reaches your peripheral tissues, the blood pressure has decreased to about 35 millimeters of mercury. And once it exits the capillary bed, it's down to like 15. You're so far from the heart. And this low pressure, it's a good thing, because if the pressure were too high and if blood flow were too fast, the capillaries would break and the nutrients carried in circulation wouldn't be able to diffuse out into the tissues. Your cells would die. So high blood pressure can easily cause blowouts of these capillary walls. There are three types of capillaries. Their names are based on their permeability. The most common capillaries that we will see are continuous capillaries. They're also the least permeable. And the squamous cells are very, very tightly packed with these very small areas of movement called intercellular clefts, right? They're not so big there in those continuous capillaries. We'll see fenestrated capillaries in the kidney, and there are a little bit larger holes between the cells instead of being little clefts. These are what are called fenestrae, a word that literally means windows. And then the most permeable of capillaries are sinusoidal capillaries. Sometimes they're called discontinuous. Sometimes they have extraordinarily large clefts. In fact, so large that we call them sinuses. And those are large enough for red blood cells and white blood cells to make their way through, right? Because there are cells being formed in the bone marrow and leaving. So these or sinusoidal capillaries are really, really leaky, right? So cells and fluids pass through based on their gradients. And this is also found, as I said, in bone marrow. And this is a picture of bone marrow here. You can see some of these are developing white blood cells, and they'll be leaving into this little venule right there.